Hello, everybody. Welcome to Horses and Humans Research Foundation Webinar Wednesday. I'm Dr. Pebbles Turbyville, the CEO, and I just want to give you a little bit of information if you don't know about us. HHRF is all about horse and human connection or interaction, and we're about exploring it and educating others about the value and relationship and connection. And we're also here to support research that helps both to thrive. So I'm going to turn it over to Molly Sweeney, our founder, so she can introduce Dr. Peters.
Thank you, Pebbles. I'm very, very honored to be able to give the introduction for Dr. Steve Peters. He's been a wonderful help for us in a program and for HHRF, and he's just brings so much knowledge and wonderful things for us. He brings an evidence-based approach to horsemanship. He focuses on evaluating and applying scientific research to guide decisions that establish best practices. He has insights into the neurofunctioning of the horse's brain, along with their practical application, which enhances the ability to interpret and understand equine behavior more effectively and bridge the gap between science and horsemanship. All of this empowers people to build relationships rooted in trust, compassion, and understanding. Through his teachings, writing, and clinics, Dr. Steve Peters brings brain science out of the lab and into the barn, helping people use knowledge of the nervous system to improve welfare, communication, and performance for both the horse and riders. For Dr. Peters, every horse is both a teacher and a partner, and every new discovery is a chance to improve how horses and humans learn together. Dr. Peters.
Good evening. Just bear with me a moment and I'll get everything up and running. All right, here we go. And I think the topic's appropriate because it's Horse and Human Research Foundation, and we're concerned with connection. And we're going to talk about the importance of connection, not in sentimental terms, but in biological terms. Molly did the introduction. Basically, my day job was assessing brain functioning in big hospital-based clinics, but I also used my knowledge and kept up with the mammalian research and peer-reviewed journal articles on horses and the equines. And as you know, over about the last 15 years, I've been giving horse brain science clinics. So we're going to go back to the very beginning, evolutionarily. And it's interesting because, Charles Darwin is supposedly known for that idea of survival of the fittest. Actually, he never really said that. And if you read Descent of Man, basically what he said was that it's cooperation and social components that are the highest form of evolution. And this little molecule, it used to be called vasotocin long before horses were on the plains. Vasotocin split and became oxytocin that you may have heard of and vasopressin. And this allowed us to be much more socially complex. What oxytocin allowed for was trust and bonding and for us to have a social blending and community. The vasopressin, that's over where it says antidiuretic hormone, it's the same thing. Vasopressin allowed us to be territorial, protect our mates, but it was designed for social benefit. If you look, these 9 teeny amino acids are pretty similar in their makeup. And to know that they are what's created the emotional architecture for social connection is fascinating. It's always been around. Here's what we know about brains. You can survive, a brain can survive alone, but it really can't thrive alone. brains were made to interact. And so the social component that allows, here you see allo grooming between these horses, and horses are designed to be in a herd. Brains cannot grow when we are threatened or when we have to constantly think of survival. And what communication and community has allowed us to do is actually live safely together, supposedly. Hopefully, that's what we're designed to do, actually. So this colt is going to be more resilient because of its connection with its mother. Not just that warm, cuddly feeling, but on a cellular basis. There are changes that take place that we'll talk about tonight that allow these animals to be more resilient to stress and to be able to learn and grow their brains. And there's all kinds of, if you don't believe a horse is social, you can turn out 3 or 4 horses on 3 acres of land and watch. They'll be sharing the same blade of grass out there when they go to grazing. So there are all kinds of behaviors for us to be aware of that allow for synchrony, that allow for connection. And they're important for us to know because when we enter their world, that's what we're doing. We're either ignoring that or we're using a natural communication that the horse already has built in. So when we step into the picture, we're reading each other. That horse is looking for micro movements and breath rates and how you move. All that's being taken in, and the horse is deciding whether that's really worth being curious about, or whether they have to hold on to a defensive posture. And it works the other way around. A tough cowboy might say, well, I don't really, whatever that horse does, it's not going to affect me. But actually, we know once we wire people up that even subconsciously, our somatic systems are responding. And I don't mean to be negative to cowboys. I know all cowboys are not, necessarily unfeeling and macho. But my interaction with my little Mustang here, if I am able to approach in a way that helps them to regulate their nervous system, they can pick up on that and we can actually regulate one another. I bring this up because if you don't stop and become aware of this, then if you're having a bad day, if you're angry, if you're frightened, and you try to fake it until you make it, that's not really going to be an effective strategy because horses are masters at pattern recognition. So what I would encourage everyone to do, I used to do this as well. I would just pick a marker, maybe a telephone pole before I got to where my horse was. And I'd say, once I reach there, I need to stop and take stock of where my own nervous system is, because that's what I'm going to be bringing into the equation. It's not just one nervous system, the horse, it's 2 nervous systems working together. When we have an optimal learning situation, by that I mean the horse feels safe, we feel safe, we have enough arousal. You have to have arousal to learn. Too much is not good. Not enough is not good. It's kind of like the Goldilocks principle. You have to have just enough. And when you do, you optimize the opportunity for neuroplasticity. And neuroplasticity is creating networks of connection throughout the brain. Now, also, what we want to do is be clear in our messages to our horses, because if we're confusing, oftentimes that creates too much. sympathetic arousal. And so that's where we go outside of that range, outside of that window of optimal learning. Now, horses' brains aren't designed to think deeply or to think abstractly. Think of them more as prediction devices. And so they have whatever's happened to them in the past is what they carry with them. And when they face a new situation, they're looking to see if the reality matches their history up until that point. If it does, then they can quickly settle if it's what they expect or they're comfortable with it. If the reality doesn't match their worldview, then they can become sympathetically aroused. And the reason that that's important to us is that if they're within this optimal window, then they can be curious, then they can explore. And if they understand, if we're clear in our messages, then they can understand what we're asking. And so this horse here understands what's being asked of it by its trainer. Sometimes if the message doesn't match, then our horses will respond. And they're not being a bad horse. They're pretty much responding to what they've learned in the past up until that point. And this is where I take issue with that idea, and I understand where it came from, that horses live in the now. If horses lived in the now, you could make 20 mistakes, you could abuse a horse, and then the next day you just start over again, but you can't. You don't get a second chance to make a first impression. So what you want to do is have as many good training sessions as possible. Your interaction, your communication, your connection with your horse. If that's good, your horse will become more and more confident and look to explore. And that's where learning and neuroplasticity arrives. This is my horse Comet, who had a previous owner who whipped her in the face, and so she began to rear. So when people walked toward her, she would automatically go into this behavior. And it wasn't because she was a bad horse, it's because of the wiring, the bad wiring that got put in there. And that wasn't the horse that did that. That was a human interaction that was negative. And so Comet could not live in the now. I had to go back and work with her past in rewire. And that's what we're going to talk about tonight, is connection helps us to rewire. And that's where we can be hopeful, is that we can actually go in and change the architecture in our horses' brains. Clever Hans here is not solving algebra problems. What Clever Hans is doing is reading that human. And the human, even though he's a professor, isn't even aware how sensitively his horse is picking up micro movements and his breathing and his posture and his movement. And if you haven't read the story of Clever Hans, I'd encourage you to do it. It's a fascinating story just to be aware of how sensitive horses are to the environment. I think sometimes we go roughshod over the horse without recognizing that, wow, we're 20 steps ahead of ourselves in our communication with our horse when they are a sensory creature. Now, in a herd, they actually share responsibility for information and for monitoring the environment. And there's something called emotional contagion, where one horse might get spooked and then they all take off and run together. But it's like an entire field of perception. So all these horses, if you look at them, are all kind of in the same window when we look at their level of sympathetic arousal. The second one from the left is my Mustang. This is his old herd when he was a wild Mustang in Mesa Verde National Park, and now he's with a bunch of boring horses that were domestic. Well, we have some other Mustangs too, but one of the things that is difficult for a horse. Think about it. If you've got a built-in security system and you can read information off of other horses, it's like pooled information coming in, and then you're isolated. That's one of the most stressful things for a horse because you're the only one left to make decisions and you really have nothing else to read around you. And so isolating a horse can, as we know in plenty of studies, and we'll talk about some as we get further along, but it creates higher levels of cortisol, creates all kinds of different hormonal changes that we'll talk about. So here's my friend Mark Rashid, and if Mark can provide a steady, calm environment, and this is what I want you to think about as well, is that you are not just walking up and interacting with your horse, you are creating in your movement, in your breathing, in your approach, an environment for your horse. So you want to create an environment that optimizes learning. And here, because Mark's able to do that, instead of a defensive posture, this horse feels confident enough to explore, and we have curiosity. And why do we care so much about curiosity? That's the big dopamine hit. Same with you. You're curious about something. You learn something. Aha, I got it. That's your dopamine hit. Your horse is no different. They have all the same neurochemistry that you have. There are differences, surely, in the brain, but they're not as large as you may think. So here's the human brain on the left and the horse's brain on the right. Some of the differences to be aware of is the human brain looks really puffy. It looks larger. And that's because we have so much tissue in our frontal lobes and what we call prefrontal lobes. We use those for executive functioning. We use those for planning, strategizing, making contingency plans about the future. Your horse has a frontal lobe. All mammals have frontal lobes, but their evolutionary niche was to be able to do what they do, and they do it well. You see this large structure here on the back, this structure right here, that's the cerebellum. That means mini brain. Look at the comparison between the human and the horse. That's balance, fine motor movement, sequencing, timing. All those things take place back there. There's actually more neurons back here than there are in the whole rest of the brain. So that tells you something about the horse being a sensory motor creature. And then there's a flap up at the front of the brain that you can't see on the human, but it's over here on the horse. I have a bunch of people's faces, so I can't actually see, but it's right around here. That flap is the olfactory bulb. And you can tell how important something is in the brain by either its location or its size. And so these large structures tell us a lot about the horse and the importance of those structures. Now, although that horse doesn't have the same frontal lobe that the human has, they have something called the cingulate gyrus. That's marked out in green here. So your marker is, here's the corpus callosum. So this is a big band of white matter, myelinated fibers, allowing both hemispheres to talk to each other. Up above that is our cingulate gyrus, and the cingulate helps regulate emotion, and it's actually a hub for taking in. It's where our horse is going to make decisions. Is there enough saliency here for me to for an example, that horse may not want to burn off calories, but it knows a mile away there's a green pasture. Well, do I really want to walk all that way to the green pasture? Now, they're not asking that question, but that decision making is being done by the cingulate. Another important piece is this is where the horse does live in the now, and that we are live wired. Everything that happens in our brain leaves a trace. In fact, after listening to the podcast tonight, you'll go to sleep, and some of those wires, some of those things that fired will actually start to make connections, and you'll be a little bit different than you were before you watched. In fact, Pebbles told me she's not charging any extra for all the dendrites we're going to create in your brain tonight. Safe zone. This is not a location. This is just a prerequisite for a prey animal to feel safe. If you don't feel safe, it's no different than, if you're a kid in an inner city school and you're worried street gang is going to beat you up after class. Well, it's pretty hard to focus on trigonometry and Shakespeare in that type of environment. And there is our split from vasotocin to oxytocin. And oxytocin, in a herd, horses have higher levels of oxytocin. You could call your horse barn sour or buddy sour, but actually what you're creating is oxytocin withdrawal when you take them out of that situation. So you need to be aware of that so that you can change the neurochemistry in your interaction with the horse. But oxytocin is that bonding neurochemical. Females have it. We studied pregnancy. That's where a lot of this early studies on oxytocin came from, and found that in women, their oxytocin levels are highest when they're lactating or right after they've given birth. And so there's some thinking that that's what helps the mother-child bond. Serotonin maintains emotional balance. And so these are neurochemicals we want to be aware of because they can help us help our horse. We can help create a more optimized environment, a safer environment. And it's not that we think it's safe. It's if we can interact with them and maintain levels of serotonin and oxytocin. Could you create oxytocin in your horse? Sure, you could. Maybe not the same way and the same extent that horse to horse can do. But if you simply go out and scratch on your horse and scratch their withers, you can actually create oxytocin increases in your horse. So being friendly to your horse is not just romantic, it's neurochemical. And what I want you to see here is that we talk about sometimes, dopamine, and then we might talk about another neurochemical. It's a whole symphony, and sometimes they're dose dependent. So you see the second one from the bottom, norepinephrine. We need norepinephrine in order to have enough arousal to learn, but too much, and then we're going to start moving toward fight or flight. So too much arousal is not good. However, if we don't have any arousal, then we're not able to focus. And these go hand in hand. The more arousal I get to a point, the more acetylcholine I have. If I have more acetylcholine, I can focus my attention better. If I have that level of arousal with norepinephrine and I'm really focused with my acetylcholine, now what I focus on and learn gives me the biggest dopamine hit. This is why if you're drilling your horse again and again and again and again, they get less and less and less dopamine. They are less aroused. They're actually more agitated. They'll start thrashing their tail, etc. And then you lose their attention and you wonder why. It's because you changed the cocktail. You're the bartender, right? They just showed up. And actually, here's just another picture of this emotional contagion where everybody is like a field, all in the same Basically, this is what a stampede is, where everybody has so much norepinephrine, and all the cows you see in the old movies run over the wagons and all that stuff, they just are filled with norepinephrine, and it becomes emotional contagion throughout the whole herd. And oftentimes in the past, where I've maybe moved a neighbor's cows from one pasture to another, it's a very slow process, and they just will walk. They can learn to do that, and you can do that with your whole herd filled with serotonin and oxytocin, and you can get a 10-year-old kid to walk trained cows from one pasture to another. But then all the neighbors want to join in, and they've been watching Rawhide and Gunsmoke, and so they're not having fun unless they're creating norepinephrine in the herd, and so all the cattle want to run out and hide somewhere because now the herd is filled with norepinephrine. So you can actually change the whole chemistry of an entire herd. And horses are often looking for synchrony. If you watch how many times they're on the same footfall, they're all moving together as a unit. And that's actually built in to their biology. Acetylcholine, we want this because it's going to enhance our learning. You're not going to learn anything that you're not paying attention to. So that's how information gets encoded. So attention encodes information. That's only part of the process. Then you have to down-regulate. So that's where you reflect and you consolidate the information afterwards. So if we're keeping at our horse all the time and they're filled with norepinephrine, they may be able to pay attention and get bits of information, but not consolidate it into long-term memory without being able to come back down. And this is what you've heard about. Lay people call it dwell. It's just that break where there's no outside interference of other information coming in and competing. It's just the information that's been learned. And a single horse. So here's Dakota, our Mustang, out of the herd, and this was his first day where we had him in panels before we introduced him to our herd. And you could see that on his own, he had to make his own decisions. He had to adjust his own nervous system, which is different than that security of the herd. So that's why we're talking about connection. False positive bias, we need to know about this because anything that is not identified, any new object that is not identified is considered a predatory threat to a prey animal. So that's why they're curious to go check something out. And if there's something that they can't identify, why they remain sympathetically aroused, because it's a predatory threat. This idea has kept them alive over time. Now, your world is actually your world. That might sound pretty self-explanatory, but we all create our own worlds. And our horse lives in a different world than we do. And one of the first things we want to do is understand the world that they live in. If we're going to connect with them and step into their world, we should have an idea of what their world is. Well, look, they have a horizontal pupil. And so they have 340-degree arc or range. They don't see very clearly, but they're so attuned to movement. They can pick up movement. They're very sensitive to that. And they actually have binocular vision in front. So oftentimes when they're putting their head down to cross a stream or step up onto a trailer, they're really looking to get depth perception. They have ears that work independently. Yours don't. So they can move them almost like radar. And they hear within a different range than we do. And it's easy for them when something is not identifiable or we've approached them too quickly or there's starting to become a mismatch between what they expect and what the reality tends to be. That's called a prediction error in the literature. So having a prediction error where you predict that things are going to be okay, and then you sense that they're not, that can be highly sympathetically arousing. So this horse, it's pretty obvious to me, is not in the best position to learn. In fact, where are their thoughts? Exit stage left. You can look at that eye and, I'm out of here. They sense things differently through smell. They're bringing in, I showed you that large olfactory bulb. I should have brought a brain up here, but my basement's filled with brains, by the way. Yeah, and then the dogs nibble on all these big knuckle bones. So if you come to my house, it's pretty scary. It looks like a physiology lab. But anyway, you can see this nostril flaring, taking in information, actually taking in emotional information. How could that be? Well, here's this big olfactory bulb back up front here, and I'll explain that in just a moment. Just some things to point out because we're going to go over them a little later. This area is superior colliculus. This is where the horse's eyesight picks up movement and processes it before the brain can. This is why your horse is going to spook and jump. This is because it's not even getting processed in the rest of the brain. Think about it. If you saw something and it came in through the optic nerve and then it went back to the sensory area and then it went to some association areas, then it went to the motor cortex. That's a long time if there's a lion coming out of the bushes. But the superior colliculus will process that visual information and immediately turn the horse's head and move it in a certain direction. Your superior colliculus would be working if I threw a tennis ball at your face. You wouldn't stop and say, well, that's a tennis ball. I'm going to move 3 inches to the left and it'll miss me. It's immediate. There's really no thinking that takes place. And it's interesting to understand that because why would we punish a horse for having built-in capability to survive? And they really don't, it's not like they did something on purpose or even have control over that. I told you things in the brain, we can determine their importance because of size, giant cerebellum, balance, timing, sequencing, fine motor movement. The thalamus right in the middle, grand central station. Everything, all the sensations that come in to the brain go to the thalamus first, and the thalamus sends them to where they need to go, with one exception. Smell. This is Marcel Proust. He is a novelist. If you've ever tried to read his books, Remembrance of Things Past, it's a big fat book. I remember as an undergrad reading it and saying, is there a story here? Because basically what Proust did, and it's interesting to me now, is that explained fine details, exquisitely. And if you look at his teacup there in front, there's a cookie called a Madeleine, a French cookie. And he wrote about dipping that cookie into the tea, and then it gave off an odor. And he tasted it and was immediately transported by this strong emotional experience that he couldn't identify, but it was strong emotional. And then he realized that as a child, his aunt would dip a Madeleine in tea and it would have that same odor. And I told you everything that's incoming to the horse's brain goes to the thalamus first, except for smell. Well, where does smell go? It goes to the olfactory cortex. It's more direct. And then it goes to the amygdala, where we're talking about emotion. It goes to the limbic system, and it goes to the hippocampus, memory. So memories are strongly linked to emotion, and they're more direct, and they're not buffered by thought. So your horse, that's what I meant, may be picking up emotions actually out of the air, which is fascinating to me. They've done research with, essential oils and haven't really found real convincing evidence except for one scent, lavender. Lavender seems to have a really calming effect. It lowers cortisol levels. So if you're going to go work with your horse, you might want to, instead of put perfume on, take a lavender bath and then go out there and wander in your pasture and do some experimentation. We're scientists. So we have all this information coming into the thalamus through an area called the reticular activating system, RAS for short. These are called afferent messages. Efferent messages are those going from the brain out to the somatosensory, out to the somatic part of the body. Incoming signals from, all the optic nerves and from respiration and from heart rate are all moving up through the brainstem to the thalamus to get processed and sent to the cortex, unless it's considered threatening, and then it's going to go to the hypothalamus and take a different route. So if it goes to the thalamus and we're keeping our horse within a certain range of tolerance, then those messages, and if our messages are clear, if our messages are cloudy and we're not making ourselves understood, confusion can create sympathetic arousal and start to send those messages to the amygdala, which is an area associated with fear. So if we can send them to the somatosensory cortex and on to the motor cortex, that's great. We get what we want. We put the cue on and our horse does what we want, and we take the cue off, for example, if you're using negative reinforcement, and then they get their release. But if they're going to the amygdala and we continue to put pressure on, then we're going to the hypothalamus and we're going to get fight or flight, and we're going to get messages sent down what's called the HPA axis that we'll talk about here shortly. So the quickest way to solve heightened sympathetic arousal is flight. And horses they're not going to be able to relax with something unidentified in their environment. So anything that looks, sounds, feels different, that's where their attention's going to go. So fighting them for their attention is really not going to get us very far. Basically, it may be a good idea to then say at that point, you know what, let's work at getting to introducing you to this thing that you haven't identified, so that if you feel it's safe and it becomes familiar, now it's part of your data bank, and then you can relax and move on. But so many times I've seen people try to force the horse through this, and all you're getting is more sympathetic arousal. So where attention goes, that's where our neural firing is going to flow. So we want to get that attention in a certain state of mind. Now this little horse, you can see, is right at the cusp of, if I were to put on a little more pressure, I'm going to send this horse into fight or flight. If I can be intriguing enough and maybe step back, and instead of putting something on the horse, actually inviting the horse to check something out, I may then move them into curiosity. So I just wanted you to see this balance point. Now we're going to talk about brain-derived neurotrophic factor. So you'll have something when people say, well, what did you learn about in this podcast? Now you have a big word, BDNF, in the literature. Brain-derived neurotrophic factor, the reason it's important is that it aids neuroplasticity. It's neuroprotective, and it allows neurons to just thrive. But here, and it aids in the reorganization of neurons. But I can talk about this here. With brain-derived neurotrophic factor, if we set up a good environment, brain-derived neurotrophic factor will then, there's these high affinity receptors They're called tract B receptors. If brain-derived neurotrophic factor can fit into those, wow, we grow dendrites like crazy. We optimize our communication in our neurons. This is the way we build a neural network. But if we put a horse under abuse or too much pressure, the BDNF will actually bind with something different, something called P75NTR. But those receptors actually will disengage connection. And those neurons that are disconnected and don't have a way of communicating, even if they can't connect on that level, they'll die off. Something called apoptosis. It's programmed cell death. Those neurons will actually prune back. So in the environments we create for our horses, we have to take some responsibility that either we can grow these vast networks in their brain or we can actually prune them back in what we do. And then we blame the horse. You stupid horse. Well, yeah, if you've pruned back the connections, then we're not going to have that big network that we need. I'm going to talk about this very briefly. I don't want to spend a lot of time with it, but LTP is something that you'll run across in the literature, long-term potentiation. And what happens is if you learn something on a superficial level, you'll get glutamate, which is the major excitatory neurotransmitter in your brain. 50% of your neuronal connections are glutamatergic. So you're using glutamate. You move your right hand, your left motor strip's firing. So that's glutamate that's going to be causing those neurons to fire. If you're learning something and you're just cramming for a test, well, you'll learn something on a superficial level. And if you look over on the slide on the left, there's a little orange ball. That's magnesium. And we have sodium coming into the nerve. This happens in your horse. This happens in you too. But let's say you've studied something for a long period of time, and now over a number of days, weeks, you're gaining more and more knowledge. Well, you'll get more and more glutamate that keeps fitting in to those receptors, and you'll blow that plug out, and then calcium comes in. Now you have a super network. You have a super network. So whenever you fire those neurons again, they'll fire almost automatically. When you become an expert at something, when your horse becomes really good at something, you've created LTP. It almost becomes automatic. Those are the things that you know so intimately. If I woke you up at 1 a.m. out of a deep sleep, you could tell me about it because it's in long-term potentiation. But you can also get long-term depression. And this is what I was talking about. I don't mean an emotional depression. I mean, it inhibits the firing of neurons. So in an optimal environment, we create long-term potentiation. That's what we want. Long-term depression, we're inhibiting neurons from talking to each other. There's one way, and this, I told you, this happens over time. Well, that's true, except you can create long-term depression on one trial. And you can create long-term potentiation on one trial in one situation, trauma. Trauma will leave you with a memory you cannot get rid of. So the amygdala will so supercharge that memory in the hippocampus that you end up with something you can't get rid of. So we really want to be careful because we don't know what is traumatic to our horse and how they're going to respond. And every horse is different with a different nervous system. So I think what I've been talking about all along is this connection, this safety, this environment that we create for our horses so that we can connect, so we can have a horse-human connection. Because you can even look at this under a microscope. If you have stimulating, challenging, safe environments, you can just, your dendrites will flourish. But look at those neurons when you have passive involvement. Passive involvement means your horse has no agency. You're going to make them do everything that you're going to make them do, and they're not given choices to learn. If they're isolated, I already talked about being in a herd where you have this connection versus isolation, which is highly stressful. And that's what we call an impoverished environment. And actually, if you look at the brain, you can see the ramifications of that. Connection allows you symbiotic relationships so that you can, I'll brush away the flies from your face, you brush them away from mine. I'll stand next to you and keep guard so you can get REM sleep. We're also learning that in the amygdala, which is related to fear, there are actually dopamine neurons in the amygdala. And if you can get those firing, then you can reduce fear. You can actually cause fear extinction. I don't mean wipe away the memory. You'll never wipe away the memory, but you rewire the brain. And so that those things that were once fearful don't carry the same emotional weight. So what would this be like? If your horse has this prediction that this was scary, this hurt me in the past, I don't want to do it, and if we introduce them to that again in a safe way and nothing happens, they actually get dopamine hit from that. Wow, I thought this was something bad was going to happen, and it didn't happen. Well, if we do that enough times, dopamine is going to help us by firing in the amygdala and allowing us to create this fear extinction. This is fairly new research. If you look, it's 2025. We've always thought these kinds of things, and I've worked with horses thinking this kinds of things, but now science gives us a lot more support. And here's a traumatic pathway. So we have long-term potentiation. That neuron's been myelinated. So now, as soon as anything resembles a trauma, that horse is going to be hyper alert, even in safe situations. Now I have to go back and use an alternative pathway and convince the horse that what we're doing is safe. And I may need, those of you who are who rehab horses or rescue horses know that you may need 100 good experiences to make up for something bad that happened in the past, so that you now have a new pathway. But the hope is neuroplasticity. We can rewire. We can make changes in the brain. Signal to noise ratio. If we're clear in our message, right, and our horse doesn't have to worry about things. If our horse is worried about things and they're not really with us and they're feeling threatened, that's going to create a lot of noise. And if there's too much noise, they're not even going to hear our signal. What we want to do is manage the noise, let them know that they're safe, make a connection with them so that the noise is lowered, and then our signal can become much more subtle and it'll be recognized. And then we can have communication. They recognize our signal and we can talk to one another in the way that we do, sensorially. Prediction. You know, if horses can predict what's going to happen, and so we can go out of our way to set things up so that they have some understanding, some cognitive understanding of what we're asking of them, then their nervous system can adjust to that through learning, if they have an understanding of where things are going. And so sometimes going out of your way, for example, the ranch horse may have a cognitive understanding of why we're side passing, because we're going up to the side of a fence and we're going to open this gate. Or the reason they're asking for a transition here is because these cows are going faster than I'm going, and I'm going to need to pace myself with those cows. So that cognitive piece of prediction, we can use that where horses feel comfortable and they have serotonin on board to maintain an emotional balance. It's in this social engagement range. It's in this safe range where horses can learn. There's no point in trying to teach them when they feel that they're in danger or threatened. And look at this. If we stress them, what are we doing? We're actually shrinking brain networks. Like I showed you, With BDNF, the BDNF will just bind with receptors that we don't want them to bind with. Here's the stress response cycle. Hypothalamus, pituitary gland, adrenal gland. This is what's called the H, hypothalamus, pituitary gland, P, adrenal gland, A, HPA axis. That's what you'll find in the literature. And the adrenal glands are going to create cortisol. Here's the same thing, emotional stress up at the top, physical stress. We see our pituitary glands, our adrenals producing cortisol. Here's the cool thing. You see those little egg-shaped structures with a GR on them that are green? Those are glucocorticoid receptors. So cortisol is a glucocorticoid. So here's cortisol leaking out into our system. But if it binds with the glucocorticoid receptor, it gets neutralized. So we're very resilient to stress. And our nervous system can handle stress if we have glucocorticoid receptors. Well, how the heck do you get those? Well, I don't have a pill for those. What you get those from are nurturing environments. It's very interesting that rat pups that are licked and cuddled a lot by their mothers, prairie voles who are allowed to mix with other prairie voles in community, in connection, they're filled with glucocorticoid receptors versus the isolated animal. And this is throughout the mammalian research. We find that if we can create nurturing environments, it makes sense. We're better able to deal with stress. So if we're isolating horses, if we're putting too much pressure on horses, we're saying you don't need glucocorticoid receptors. I'm just going to fill you with cortisol. And then the horse responds in a certain way, a defensive way, and we blame the horse. If we're going to be a good partner in this connection, we really need to understand this because we can benefit both. You know, the welfare of our horse really depends on how we start to think about how to really work with their nervous system. Now, this big green structure that bends around here is called the BNST, bed nucleus of the stria terminalis. I don't know why we give you these words so you don't know what the hell we're talking about. But we could just call it green structure right here. It goes all the way down and hooks to the amygdala so you can figure out what that does. Once this structure gets activated, that horse is always in hyper alert state. That horse can't find its way back down to homeostasis. It carries around this constant hypervigilance. So if we push a horse to that point and they don't find a way down, this structure will stay excited. And that's not really what we want, because then we're going to carry around worry and not feel safe much of the time. Now here, before on my other slide, I showed you a structure that went right here, the cingulate. And I said it had a role in helping regulate emotion. Here it's not defined. Yeah, to my chagrin, I learned early on in looking at brain surgeries that those brains are not color-coded like my textbook. So they're a little harder to find those areas. But here's our anterior cingulate. It's in blue. And it's producing something called GABA. What is GABA? Gamma-aminobutyric acid. Basically, I told you glutamate's the major excitatory neurotransmitter. GABA is the major inhibitory neurotransmitter. And once our horse gets used to regulating their behavior, they've been challenged and then been allowed to come back down to homeostasis. If they continue to do that oscillation over time, they can produce GABA, and the GABA is going to the hypothalamus in inhibiting, because it's an inhibitor, inhibits the HPA axis from creating glucocorticoids. So we can actually outfit our horse in a way that they can use their anterior cingulate to self-regulate their own behavior so that they feel safe. They don't actually need you And that's actually a good thing. They don't need you to self-regulate. They'll get a little excited and then they come back down. They get a little bit excited in a new situation, and then instead of going further up and having fight or flight, they're able to self-regulate. And part of that process is because we've worked with them and created an environment where they feel they can self-regulate and they create their own neurochemistry. This is the myelin that I talked about. Basically, if you fire a neuron and you fire it enough, you can cause these things called oligodendrocytes. It'll excite them. They say, something's going on here. There's a lot of excitement. These neurons are firing. It arrives at the scene and starts to wrap those neurons in myelin. The problem is that you want to be precise in that. If your horse is learning things and within this window of optimal learning, then we're going to have a lot of myelination and things are going to happen automatically. But you can also myelinate things that you don't want. So when you're starting to see, my horse doesn't understand what I'm asking, I don't think I'm clear in my message, they're too sympathetically aroused, that's where we want to back off and rethink how we introduce things, because we're going to myelinate those things whether we like it or not. And that's what's rewiring about the brain is all about. There are different ways we do this with neuroplasticity. One is we can create brand new synapses. This is new information. We can weaken the ones that we don't want. Well, let's stop doing that. You know, if this is causing problems for the horse and I, then I don't want things taking that pathway. I'm going to have to weaken and stop doing those things that create problems. We can weaken synapses, strengthen the good ones, and something we didn't even know about, but we're getting more and more understanding about this, neurogenesis, actually creating new neurons. Not everywhere in the brain. There are certain areas like the dentate gyrus we don't have time to go into, but just know that we can actually create new neurons in the brain. And we want these brains firing and wiring. And here's a picture of what that looks like. We want a dendritic forest in our horse's brain. We can set that up by creating curiosity and exploration. We want our horses alert and ready to learn. Is this horse too sympathetically aroused? No. Look at its mouth. It's not clamped shut and gone dry, right? So the parasympathetic fibers from the ninth cranial nerve, the glossopharyngeal nerve, are still allowing this horse to lick and chew, but that horse is very alert. So we know emotionally they're in a good place and they're focused and with us. So this horse, if we teach it something new, is going to get such a big dopamine hit, they're going to be at the fence saying, what do you got for me next? Isolation does pretty much the same. It's sensory deprivation. We're not giving the brain enough information. They need connection. They need touch. They learn it from each other. Look, here's this thing called synchrony that I talked about. Look at these foals and look at the mom's footfall on both of these. They're different footfall, but look how in tune those babies are. So this is something to understand as well. We can use synchrony to work for us. Basically, what that would mean is when our horse has these natural rhythms and we can be attuned to them and pick them up, then we can attune our nervous system to theirs. Think of it as a rider. You know, you've seen riders, I'm going to make this horse do something, and they get out of balance or they're trying to balance on their reins and they pull their horse off, and the horse is still trying to connect with them. But if we can connect with that horse and move with that horse in such a way that we're in rhythm, that actually feels good to the horse. That creates serotonin and a balance and a connection. Now, I've been way too industrious, and I have so many more slides to go into, and we could go into this at a much deeper level, and I appreciate your attention. Some of this we're going to pick up at the HHRF conference, so I hope you'll come, and I hope this has whetted your appetite for understanding your horse at a deeper level, and yourself. Because we all have brains, we all have this neurochemistry, and we're a working relationship. That's what makes Horse Human Research Foundation. So cool because it's the horse and the human interaction and connection. So with that, I'm going to draw this slideshow to a close. Maybe we'll handle a question or two if I can. And thank you very much.
I want to tell you, thank you so very much. I'm going to stop the recording and then we can have a couple of questions.